there's an I here, there would be an I here. Remember, the trick was to find those intervals and then arbitrarily cut them in half to get the cover so that we have slop. We can still wander around with another half unit of epsilon there and still stay inside this guy, which was in the original cover. So that's what we're doing. If this is true, it means he's in there. And of course, that thing would be inside one of the original cover elements. So what we have to do is show this. But y minus xi is equal to y minus x plus x minus xi, right?
Yeah.
This is delta, and x of course is in one of these guys, right? We said he's in there. He's in one of them. So this is at most that, and right? And this is less than that. So this distance must be less than two of those things, which is epsilon I. But that's equivalent to y being in the original epsilon interval. You want me to write this up? Oh. Is it okay? All right, you sure? Okay, come up here and explain that to me. Hold it, go through it again. I'll write it up if you want. You want me to write it? Okay. I don't want to leave you hanging with some stuff that's not exactly cool. So anyway, that's the existence of a Lebesgue number. For a compact set with an open cover, the Lebesgue number exists, and then you can go and win these proof of the Heine theorem. Okay, so all of this stuff that we've been building up to, why do you need Heine's theorem? To define properly the Cauchy and then the Riemann integral. Here's what you need it for. Here's the function you'd like to integrate to in the law. And I'd like to integrate from A to B. Okay. F of x is continuous, which means on a closed interval AB, it's uniform. That means if I insist on the variation in the function being no more than epsilon on a subinterval, I can come up with a single delta that will work for all the subintervals, right? Or wherever I am on the graph. It means that if I want the vertical separation to never be more than epsilon, theoretically, so the vertical separation here is never more than epsilon at a time, right? Means I can bring these things down and find corresponding deltas, and then take one delta for them all. You'll be able to find the smallest one, right? So there exists a delta of epsilon such that if, well, you know, x minus y is less than that thing, it implies what? That f of x minus f of y absolutely is less than epsilon. So there's a magic delta, and if I keep my subintervals less than delta, the variation of the function will never be more than epsilon. Okay? Why could I not do that if I didn't have uniform content? It would mean that there'd be a delta for each subinterval. But this thing allows me to go find one delta as long as I'm smaller than it. And I might have to put an extra line or two here to stay smaller than the delta. You know, where the function is moving the fastest, the most vertical there, the epsilon has more leverage relative to a given horizontal displacement. So if I stay less than a fixed delta all the way from A to B, with the subintervals, the function will never vary on a subinterval more than epsilon. I could not do that if I didn't know it was uniformly continuous. Just continuity would give me a delta for each subinterval. And in principle, I might have to take the sup or int for something like that, and I wouldn't be able to control it.
So that's the theoretical foundation for finding a fiber function.
Yeah. Oh, yeah. Yeah. I mean, the next thing we're going to do is show that any two partitions, if one is a refinement of the other, the Cauchy sum over the two partitions doesn't vary more than epsilon times the length of the interval.
Yeah.
Yes, sir.
You're saying if you had like different deltas on the interval at different like intervals that you took, it might be really to take those to try and find like something.
Yeah, I could not. If I had an interval upon which the function was continuous but not uniformly continuous, I might, suppose I tried to integrate 1 over x on the open interval, open at 0 and closed at 1. So 1 over x. Okay. To get a decent Cauchy or Riemann sum, I can certainly find deltas at each one of these interior points here so that the variation of function is no greater than epsilon if I stay below the delta that's appropriate for that point.
And as you get closer and closer to 0,
So what will happen, Matt, is the deltas will get infinitely close here. Okay? And then I have a problem finding a delta that will work across the board because I need to always take the sort of the sup of the deltas and or the int with the deltas, and they're getting so small that that would be 0, and suddenly I'm in big trouble trying to define the sum. So of course, this is continuous on 0, 1, the half open interval, but it's not uniformly continuous. So you need uniform continuity to sort of put a floor under the deltas that you need. Once you pick an epsilon, you'll come up with a delta that works for all points on between A and B, right? Of course, if you change the interval over which you're integrating for a fixed epsilon, the delta will be different. The point is, you can find the delta of epsilon for a given interval of integration and a given continuous function. It's closed. So Heine's theorem justifies that. Sorry, choking over. It's choking me up. All right. So back to this picture. Let's make a Cauchy sum. What's a Cauchy sum? Let's call it S sub P, where P is the partition. And it's something that looks like this. The sum from I equals 1 to n f of x sub I minus 1. It's the left endpoint that we evaluate the function at, and after we partition the interval AB into n subintervals. How many partition points would there be? N plus 1. N plus 1 partition points, n subintervals. So I go right, and then delta xi, which is what? xi minus xi minus 1. Okay, so that, and of course, the partition P means we have picked n minus 1 points interior to AB. Add A and B to the partition, that gives you n plus 1 partition. Okay. So we may pick let's call this SP1, SP2. So different partition. Different number, partition points and everything.